Okay, so welcome for the sake of the recording. This is a course on advanced artificial intelligence method for chemistry. Okay. So the first thing is that I would like to tell briefly about my so the research topic of my group, mainly because most of what I do is related to also what I teach in this course. So I think it gives a good introduction. I will give an introductory lecture for the faculty in about a month, or a bit more than a month. It's December 11. Probably there will be announcements around. So that would be a little bit more in depth on what I do. But for the sake of this introduction, I want to mention that I've been busy with so-called interpretable machine learning, and one of the aim of this course is try to characterize what we could mean by interpretable machine learning. At the moment, we are a little bit in the Wild West scenario where everybody uses the interpretable moniker for what we like, mixing pure, say, computer science with physics, and so sometimes it's very unclear what that means. In any case, what I typically like to look into are models that are, I call them glass box as opposite to black box, meaning something we can look into. And just to give one example that is kind of our flagship result to some extent. So if we want to predict if a material with a certain composition, maybe X3, crystallizes as perovskite, as you see, I'm more towards materials than chemicals, but hopefully we can understand each other anyway. So the idea is that if you just give the composition and you want to predict if the material will or not crystallize as a perovskite, in this particular work we didn't distinguish the different perovskite structures, just yes or no, and then we set up a machine learning algorithm that would give as an output an equation, or actually an inequality in this case, because it's a classification. So there are things, so if you squint, you see the indexes X, B, and A are related to the chemical formula. So you give the chemical formula, you have a table somewhere that says that's related to that particular element. You have certain radii, these are called Shannon radii, it doesn't really matter, it's just a lookup table that says this particular chemical element has this number here. You plug them into a formula. If the overall thing is smaller than a certain number, you get a perovskite. Otherwise, you don't get a perovskite. So the point here is that that inequality is found by a machine learning algorithm, right? So this is this sensor we try to explain. This model is interpretable because we see the constituents. We can also do some mathematical analysis of the equation so that we can understand limits, asymptotic behavior, good old physics or mathematical physics, and then say, okay, so then we understand more or less what is going on. Another aspect of my research is a word that in plain English is very similar to interpretable. It's explainable, and I will try to convince you that these are two completely different things. Not the whole literature agrees with me, but as any kind of definition, literature will discuss at length if things are different or not. So this is related to deep learning. So a big part of the course will be about deep learning, and then we ask our question. A deep learning model is kind of the prototype of the black box because it is too complex to understand what is going on. Still, you can probe the model itself. At some point, you have to think when you have a complex model, it's more like you do an experiment on the model and you try to get out something, even if you don't understand every single gear and inner machinery, you can still understand why the model has behaved in a certain way and why not. So this is in the realm of explainable machine learning and is typically related to deep learning. So in practice, in my group, we have been looking into interpretation of microscopy image. So if you have some, okay, it's very faded with this light, but if you have some kind of scan image of some grain boundary, I mean, the human eye would say, okay, there is a boundary there, and we train a network on the crystal, on the perfect crystal phases to be recognized, but we actually use more information on the uncertainty on the nectar. The map that you see there is where the nectar doesn't understand which crystal structure it is seeing in the inputs, and this is exactly where the grain boundary is. It doesn't have to be there, but it's. So we didn't train to recognize grain boundaries. We exploit the uncertainty of the model in order to look for interesting things. So this is one, field of research that I have, and another one is not related strictly with machine learning. It is my kind of previous research that is still very active. It's say enhanced sampling method for studying phase diagrams of materials, and so the idea, so that is a very recent result where we have the phase diagram of silicon surface in a hydrogen atmosphere. So we just say, okay, let's not have any assumption of what happens. We just have a termination of the silicon surface, and we want to see a different pressure and temperature of the system, which kind of structure you get, including disorder and order structure. And this is methodology that we have been, I would say, fine-tuning. We didn't invent very much. It's just that we exploit scalable computation, so heavy parallel kind of computation. And then we can infer full phase diagrams of systems. The machine learning here is also present in the analysis of the data and in the usage of machine learning potentials that of course we would like to use in order to have accurate description of the system. I will not insist in this course too much in an application of machine learning for potential, because I think it is first of all, according to Professor Essen, there is already a course that goes a bit in detail about that, and my personal thing is that it's a little bit overhyped. Meaning, okay, we can train machine learning models that mimic ab initio potentials. Nice. But that's just the beginning. That is nothing. It's just to say, okay, now I have something faster than density functional theory or sometimes more advanced methods, but we still need methods to sample properly the configuration of space and so on. So this will not be in this course. It's something I like, but cannot do everything in one course. And final point, just in case you're interested, especially as a PhD student, I'm very active in the business of findable, accessible, interoperable, reusable data. So the FAIR data idea, in particular, I am part of this FAIRMAT, that is the say German Ministry of Data Infrastructure funded consortium for the FAIR data in material science. So maybe you know about NFDI for Chem, NFDI for CAT, and so on. So those are other sister consortia that are related to other fields in physics and chemistry. The FAIRMAT is more related to materials, especially the, say, fundamental description of materials, more on the, you have also Matwerk, that is another one that is more on the engineering side of materials. And we have been developing database that is called Nomad for storing at this moment more chemical than materials data. So we have a lot of information on molecules. Okay, so this is, I will essentially not touch the last 2 points in this course, but just that you have pointers in case you want to contact me for any reasons. Okay, so general kind of overview of why we use artificial intelligence in material science and in chemistry. So typically we want to do analysis and predictions for materials. That means that there are two main let's say subtopics. One is predicting properties directly from the composition and maybe giving some rough information on the structure. So let's say if it is a certain crystal phase or certain point group, and this goes into the under the name of materials informatics. An example is the application that I showed at the very beginning. So this predicting if a material crystallizes as a perovskite or not from the composition. And then we have predicting properties from configuration or ensemble from configuration that goes under the name of surrogate modeling. So the idea of the first topic is that we do not have a model. So we try to infer a model from the data. So in principle, we know what's going on, Schrödinger equations and so on and so forth. We have statistical mechanics. We have the general framework. We may believe that there is a way to connect the properties to the composition and structure, but we essentially do not have a model. So we are inferring model from the data. The other case is where we have a model, we want to make it faster without losing accuracy. So these are conceptually two very different things. For the machine learning, it doesn't really matter. It's still inferring a predictive model from the data, but it could matter the way we design the algorithm. If we know a lot about the model or if we don't. Another subtopic, two other topics where we are kind of predicting something new to some extent, and then we have the subtopic in which we interpret experimental kind of results. It could be also from simulation. It doesn't have to be actual experiments. It could be computer experiments. So we have so much information, trajectories, and a lot of things, and we want to find some pattern. And indeed, this interpretive measurement is typically under the field of pattern recognition in artificial intelligence. So people use heavily methods for pattern recognition in images or time series, and this will be definitely a topic in this course, both images and time series. So in general, one wants to do materials design besides predicting properties. That means that we may want to look for a certain so which structure would give a certain property, or just to make it a bit more clear, so elements-oriented design, where we want to look for a certain composition, sometimes with fixed structure. So we say perovskites, they have a kind of a scaffold structure, and then we change the composition to look for important properties of our interest, or other kind of pattern structures that you just say, okay, let's just change the composition, and let's see if the composition exists in that structure. Let's see if the properties are of our interest. And in general, we have the inverse design idea, in which we try to find the materials or the chemical that has a certain property or set of properties. Sometimes it's just, okay, you want to optimize a given figure of merit, but you give conditions that it doesn't contain certain particular chemical elements, or there are some other physical properties that it is stable in a certain pressure temperature range, and so on and so forth. So often you do multitask optimization. That is what we will be looking into. So the typical challenges that we have in material science and chemistry is that we don't have too many data. So sometimes in chemistry it is better than material science because you can to some extent enumerate say all small organic molecules, and we have already databases with certain properties that are systematically calculated or measured over small organic molecules. But of course, as soon as you go a little bit more complex and you want to look into macromolecules, the problem is as complex as for materials. So roughly, complexity is an interesting issue, difficult to measure. And then so in short, we typically have not much data if we compare it with other applications outside science, where you have all your say social network kind of information when you want to train a language model. I mean, all the text in the internet for training your language model, all images from all the social network and similar, be it legal or not to harvest them, they are used. So you have almost infinite amount of data, and with essentially everything that you ever want to see for training the model. In chemistry and material science, we typically do not have enough reliable data. So we have to move with the small data problem. The other thing is that, yes, the data also have to be reliable, and the dual thing is that the model has to be accountable in the sense I use accountable now to make a kind of more general, interpretable, explainable, and so on, so that you have a way to understand if the model can be trusted in a certain region of the input space that you have not used before, right? So in general, it is nice to have a model that interpolates. So basically, you query the model more or less in the region where you have trained it, because you say, okay, I don't want to have a specific model for every new set of data and do every time an interpolation. So you have a kind of general interpolator, and that's nice. But most of the time you want to extrapolate, so you want to go outside the model. And if you think science is all about extrapolation, right? So we see something and then we say it should work also outside the specific observation that we have done. And we think we have encountered the fundamental law of nature when we know it is universal, or at least we know exactly where it can be applied. So we would like to be able to query models and understand a little bit how far they can be trusted. In particular, we would like to understand if an output can be trusted without an extra check, right? So every time you get a number or a prediction, you have to check, it was correct. Nice. But sometimes you have no way to check it before you make your decision, right? Could be kind of morally important. You have to decide whether to act on something that could be life or death for somebody. In our field, typically may not be the case, but it could also be that you have to decide whether to synthesize a new material without knowing with certainty if that would be fulfilling the expectations. So you need, but synthesizing the material could be expensive from an environmental point of view. So still, it comes back to be a kind of moral choice in which you want to have a little bit of handle before you make wrong decisions. And then, then you have the interpretability, explainability kind of conundrum. I will try to address during the course. So now I want to relate a little bit this kind of general workflow to the processing, structure, properties, performance, overall idea that we have in material science and in chemistry. So we kind of bit computationally or in practice, we have some processing parameters. So we generate some kind of materials or chemicals that will have a structure. Then physics tells us that from structure we get the properties, and then a kind of subset of these properties would be the performance that you are actually interested in for our system. So there is no sharp kind of distinction between performance parameters and the properties. They are by all means properties of the system. Sometimes the performance is more towards the device, so where the material, the molecule that we have fancied is already in a kind of application scenario that has a certain setup, and so we measure certain properties. So this is the kind of direct flow. Here I add that if you include computation, you typically go more into say, okay, I have a certain specification of a material or a molecule, or in general a chemical system, and that is related to a structure. This is important because sometimes we really go through databases where we select all materials that are in a certain class, and then we evaluate the structure, the properties, and we look for the one that has the best performance, and sometimes we stop there. Of course, to really do the material, you have to synthesize it, so you have process parameters, but sometimes you do not care about this step. It's like, okay, the material may exist, and then I go downstream with the workflow. So the machine learning starts being interesting when you can go backwards. So if you can infer structure from properties, so you say, okay, I still maybe probably move in a certain class, but I can say, okay, let me find a particular structure that has a set of properties of my interest, or I go directly to, say, the chemical formula in some sense, or some specification that help me identify the material in a database. Ultimately, you want to go from the performance to the material identification. So this is the red arrows are all the attempts of doing this kind of inverse design. And not much explored at this point, at least until maybe 4 or 5 years ago. It was hardly touched that you can actually find a material and have also the synthesis parameter, right? So because you or at least to know if a material is synthesizable or not. But as everything, if there is a relationship, it could be learned, and if you have enough data, right? So this is so the let's say this new arrow from the material to the process parameters is kind of now getting a bit more explored, especially with generative models, as I will try to show, because essentially you don't really go from the material to the process. You just sample the process until you get the material that you wanted, right? So this is the general idea of generative models. But you do it essentially at zero cost because you don't really synthesize the material, except that, of course, electricity is not for free. But that is. I mean, I don't want to joke on that. That this is some kind of topic that now is more and more present. We have already protocols to say, okay, you should always say how much you have spent to do in energy terms to do a certain prediction with computation and machine learning, because it's could be intensive, and you may claim, okay, this was much faster than and less expensive than actually do it for real, but that's not given when you have huge transformers and language model used very intensively. Okay, and the last one, sorry, I pressed without commenting, is really to say, ideally maybe that last arrow should be thicker, because this is essentially the ultimate goal of the whole design, chemical and materials design future industry. I would say you go directly from the performance to the processing, right? So you say, okay, I want a solar cell, so an organic photovoltaics that has performance in this range for all my important parameters. How do I do it? So I have the position machine, and just tell me what chemicals I put into the input and what are the processing parameters. And we have few examples in which this has been done as a kind of very pioneering work, but of course to do it let's say routinely is the near medium future challenge. And yeah, KIT is really one place where to be if you are interested in this, because that's one of the main reasons I came here. I'm interested in looking into these things, and we have experimental group that are setting up robotic laboratory to do this in practice. Okay, so the so the topics now, to get more specific, of the course. So KG is a knowledge graph. I try not to use abbreviation without explaining, but yeah, it didn't fit, I think, on the slide, or probably did, but I don't know. Anyway, knowledge graph of the content rather than just a table of content, because there are connections. So we start with some preliminary idea, terminology, just to be on the same page when I say I use one term versus another, and some recap of the very important concept from basic machine learning that I really think they are. I mean, I want to be sure that you know for the rest of continuation of the course, because otherwise, yeah. It could be awkward if I think you know, but and you have never seen that. Actually, the first will be today, if yes, time permits. Yes. So that is just to get out of so to solve the mystery is the variance bias noise trade-off. That is kind of the very basic of machine learning. So statistical learning, to be more specific. So this is one basic concept that I want to be sure you all know. So then I will, so topic-wise, I will spend a lot of time with advanced deep learning. So assuming again that you have seen already the general so-called multi-layer perceptron, so the kind of generic neural network architecture. I will recap in any case, because some important concepts are there about how they are this model are trained, that are recurrent to all the other more advanced architectures. So, but we will look into convolutional graph networks, recurrent networks, and kind of evolution of recurrent networks that use the attention mechanism, and they're using the transformer technology. That means that I will talk a little bit about large language model, but yeah, in the context of this course, I will be just giving the pointers. I will not get too much into your so even the little that we know about the large language model, that it is actually shared by the companies that are training them, would be enough for maybe a couple of courses. We don't know all the details, but still, technology-wise, there is a lot. There would be a lot to say. So I will just show a little bit how we go from a basic architecture for learning time series into a modern transformer where the time series is now language. So I kind of very special time series. And then, oh, low battery. I forgot to put the. And then another important topic in deep learning is unsupervised learning. So we have the basic architecture that is called autoencoder, and then we go to modern generative models that certainly have used generative models. I will try to explain what is the basic idea. This is mathematically they get very complicated, but I will try nonetheless to explain how they work. And this is for the deep learning part. Then I have a part that is still advanced artificial intelligence / machine learning, where we look at models that try not to use not so many data, so they are built to give relatively accurate models with few data. These are sparse methods, in particular a set of, it's not a subset of sparse methods. Symbolic inference, we can combine symbolic inference and sparse methods in order to train models with few data points. Symbolic inference, the example was in the very first slide, so where I was showing you that we learn an equation or inequality directly from the data. And then I will generalize to the so-called physics, chemistry-based AI, in which we use everything or a subset of everything we may know already about the particular problem at hand to constrain the search of our model. So this will be at different levels. We can prepare the data that they kind of suggest certain symmetries, like, okay, we already know that something is invariant with respect to something. So we give this information somewhat indirectly in the data. So we present mirror images, rotations, and then we just map into the same. So this is a way to give informed learning. But more interestingly, we can bias our search, so we can construct our model so that it has to obey certain symmetries, certain conservation laws, and so on and so forth. And also in the optimization itself, so the moment we have set up the constraint, we can exploit physical tricks or constraint in order to force the model to optimize into a physically meaningful solution. So this is, the name I think was first used a few, like in 2019, really physics-based AI. It has been in the air for a while, and now it's becoming more and more important in the very recently. So I think the number of entries, if you look for physics-based models, it is increasing. So the white space in between is for general concepts that I will kind of touch during the course. So in general, I will kind of try to present examples that are related to chemistry and in general materials, and this is typically done by from the point of view of the research, is to design descriptors or to look for descriptors that are specific for chemistry and materials. Then there is the idea of self-driven learning. So this is related strongly to these robotic laboratories. So the idea of design new materials, where at the very beginning one may have very few data points, and so part of the algorithm is machine learning is always trying to predict properties for new material, for new data points, but a subset or a kind of slightly different topic is to design models that suggest new data points that could be either because you're going in the direction of optimizing your system with respect to some properties, or you want to improve your model. So the kind of meta algorithm has to detect where the trained model is more uncertain, and it looks for new data points where the model is more uncertain. So the kind of keyword here is uncertainty quantification. Again, another thing that is used with slightly different meanings in different subfields. So in general, we want to have models that have a good modeling of their own uncertainty, so that they can suggest how they can improve. And then there is this idea of interpretability, explainability, and then I add the C word, causality. This is another topic that is a bit delicate to touch, because again, so the main reason is that these words are loaded from the point of view of common language and kind of philosophical history. So in order to do some progress from the point of view of understanding from a scientific point of view, we need to characterize these words. So also causality has some kind of way to be measured, so that we can go from a purely predictive model that is basically capturing correlation in the data to something that can check if there is a kind of causal or not relationship, or which kind of causal relationship is between the input and the output. Okay, so these are all the aspects that I would like to touch. And then I move directly, so basically I'm now in the preliminaries part of the graph. I want to do a little bit of terminology. So far I've been using mostly artificial intelligence and sometimes say artificial intelligence / machine learning. Here is an attempt to say, okay, what is what, even though at the end, nowadays I would say artificial intelligence, machine learning are essentially the same for a very specific reason. So let me tell. So in general, we call artificial intelligence, so we divide the artificial intelligence into narrow AI and general AI. This is already probably a confusion, especially if you look into the news. So the narrow AI is this set of, so the theory and development of a computer system that perform tasks normally associated to human intelligence, like perceiving, classifying, learning, abstracting, reasoning. So this is something that has been around since we have had computers, even slightly before. We actually had computers, but as soon as we had computers, so essentially after the Second World War, people starting designing artificial intelligence algorithms or systems that try to reproduce human kind of tasks. So anything that tries to reproduce one of these kind of tasks is part of artificial intelligence, but it would be the narrow artificial intelligence. Then you have the general artificial intelligence, that is an algorithm that is fully autonomous in learning and doing all the other tasks, including acting, so that at some point it will be doing that. And so as you certainly know, when say deep learning started again to be a very important field in artificial intelligence, that happened in the early 2000s. There has been a period in which deep learning was essentially abandoned, first for mathematical reasons, because under certain premises, deep learning, so actually neural network couldn't do some tasks that other algorithms could do, then somebody demonstrated that actually with deep learning, so many layers you can do it. But then there was another period in which deep learning was abandoned because essentially we didn't have the hardware to train the models that were complex enough to perform the task that we wanted. So it was a very, very technical problem that was kind of eventually overcome. So now we have methods to optimize, and we have the architecture, the hardware to do that. And so since we have the new spring of deep learning, we started thinking about the general AI. And even more when we had the transformers and the language models started being more successful. We had kind of expectation that we are close to some kind of general AI. And here I stop, and my personal people to go to when I want to hear something that is informed, because Ben Goertzel and Joshua Bach are computer scientists, but they know enough about the philosophy part in order to say always informed thing about. So I don't know if you know them already, good for you. Otherwise, take note, and everything that these two guys say is worth listening to. I'm not saying that whatever everybody else is not worth, but it can be more dangerous. So at least whenever they talk about general artificial intelligence, they know and they define exactly what they mean. And in this case, then when we talk about general artificial intelligence, there is a tension between people that try to understand what is intelligence and maybe even consciousness in computer science and philosophical terms. So they really would like to understand what these things are that could help understand what human or animal intelligence and conscience is. And so one side of the tension, and the other side of the tension is companies that want something that works, right? And sometimes we don't see too much this tension, but it's huge, because one thing is having a model that works most of the time, and one thing is understanding what evolution and biological intelligence can do versus the artificial one. Okay. Most of the time I will do, not most of the time, but often I will do classifications, and every time one does classifications, we should remember the kind of, how to call it, so from the animal world, one being that reminds us that the classifications are as good as as they are, because of course this mammal has a beak and has so it lays eggs, but it's still a mammal. So yeah, be careful with classifications. So that's a platypus in case. So more classifications. So you very probably have heard about supervised versus unsupervised learning, but before that classification, that will also appear in the next few slides, I like to do a kind of more abstract distinction between two kind of model choice that we can have. One is called confirmatory analysis. More technically, it's called predictive induction. That is, so the idea of training models, or even without the artificial intelligence part, it is proposing models that predict certain properties of a system. So scientific method goes into confirmatory analysis. That is, we think at models that make prediction on reality, and the data are somewhat a part of the game, so models are empirical in that sense. And then we have the counterpart that is exploratory analysis. So this is like the kind of pre-scientific part in which we look into regularities in the data. So so the scientific process, the scientific method process, has a part that is not often highlighted, in which we kind of freely look for regularities in the data, and then at some point we come with an hypothesis, and then we design a confirmatory analysis experiment in which we try to predict something, and then if it works good, we can continue. If it doesn't work, back to the to thinking about hypothesis. But the exploratory analysis is this kind of free analysis that can lead to hypothesis. And we have methods to do this kind of exploratory analysis, also known as descriptive induction. So these two fields, so you typically have regression and classification and confirmatory analysis, and some more mysterious methods like clustering, dimension reduction, or even more mysterious subgroup discovery. So to find a subset of data that have a certain thing in common, more or less, without too much hypothesis. So this is a kind of broad distinction in what we can do with data. And the moment we introduce machine learning, we have another distinction, but we come in a second, the supervised versus unsupervised. And then I come back trying to convince you that it's not exactly the same. Supervised versus unsupervised compared to confirmatory versus exploratory analysis. So machine learning is a subset of artificial intelligence. So it needs to have the learning part. So we need to have algorithms that train models that improve with more data. So this is a kind of a requirement of machine learning. And actually, again, I use also here statistical learning. So statistical learning is kind of the superset of machine learning. Machine learning is statistical learning on computers. So essentially, they are equivalent, because we do all statistical learning on computers, except very, very, very few kind of didactical cases. So, and typically for machine learning, one needs the concept of regularized regression. So there is something that penalizes too complex models where this is not required by the data, and I will try to explain what this means. So as you see, machine learning is a subset of artificial intelligence, because you can have artificial intelligence systems that do not have any learning. They are essentially disappearing, or maybe they have disappeared since quite a while. But so I showed a knowledge graph. So an approach to do artificial intelligence is to kind of build a priori a knowledge graph and decide that every decision can be mapped into typically a binary tree, so that you and if you code that binary tree to do any kind of decision, you can achieve some kind of intelligent behavior. And this has been done extensively in the past before methods to train machine learning algorithm became more popular. By past, I mean maybe 40 or even 50 years ago at this point. Yes, okay, definitely in the last century. I think they are essentially disappeared. But now when we say, okay, now the physics informed or whatever informed machine learning is a way to reintroduce this kind of a priori reasoning before we build the model. So we may think that you have the kind of completely machine learn approach, in which you say, okay, I don't know anything about the data, the field I'm learning, I just have the data and just make a model. So you may have heard that, so there are some classes of machine learning algorithm, including all the deep neural network that are universal approximators. So basically, it ensures that with enough number of parameters to make it short, you can approximate it everything. So any function, any input-output relationship that is well formed can be learned from the data, having enough data, right? So that gives sometimes the kind of presumption that, okay, then I don't need any a priori knowledge, I just give data, and then at some point it is learned. Things like large language model, probably until DeepSeek, were exactly the implementation of that. So we have the fancy new architecture, transformers, I will try to explain. I just give data. And that at that point, the breakthrough from especially GPT 1 to 2 was just more data. So there was no extra ideas. It was like, okay, now we can achieve, so we have data in some ways that not all of them legal, and then since the machine has seen everything, that will be, but there is nothing there. So there is no information about any logic or any well, not to mention any moral rule. They introduced some kind of filter afterwards, of course, because it was for the public, so they wanted. But that was as a a posteriori filter, right? So there is a kind of raw output that we will never see outside the companies, and then there is a filter that avoids anything that is racist or pornographic or whatever, right? But the models didn't know anything about that, and that doesn't know anything about that. With DeepSeek, things became a little bit more complex, and I'm not even sure that I follow what is going on, because you can introduce now more information about the language model, but anyway. Okay, so machine learning. Back here to regularize the regression. Now, here, when we introduce machine learning, you really have the distinction between supervised and unsupervised. That is, in the supervised learning, you predict labels that you have. So you have the data, you have representation, and you predict labels. And the unsupervised, essentially, you do not have labels, or you forget about the labels, and you try to see if there is a structure in the input space. So if you can represent the input space in a lower dimensionality, if you can find that there are groups of data that are that appear together, and then maybe there are areas that are not visited at all in the input space. So this is the subset of methods that called clustering, and then you have other methods that are related to unsupervised learning, outlier detection, and so on. So this distinction is not exactly the same as exploratory versus confirmatory analysis. You can have exploratory analysis that uses labels. So basically you're trying to find not much prediction, but you want to find structure in the input, but knowing the labels. That is a little bit strange, but it is also something that it is used in data analysis. And then there is an aspect that is called reinforcement learning, that is more related to what we may be interested when we want to do design, so that you try to start with small data sets and build an increasingly large data set. So for the reinforcement learning is how at least the original, AlphaGo and well, more like AlphaZero was working, so that you just give a very basic constraint, and then the algorithm is building its data set while learning the solving algorithm. So if it was Go or chess, it means that you just give the rules, and then essentially you exploit the fact that the algorithm can play billions of games in relatively short time, and then learns from the data from the games, but will the extra bit with respect to supervised learning is that it builds the data set on the fly. It doesn't exist before. Okay, last bit of taxonomy is the subset of representation learning. Yeah, the contrast is not very good. So learning algorithms that learn the representation and the predictive model. So now all the deep learning algorithms go into this class. So it might seem a little bit unnecessary to make this distinction, but methods that are not deep learning typically do not do representation learning, but there are other methods that are not deep learning that do representation learning. So the idea is that you start from a given input representation, so you have to kind of present as a numerical kind of input anything you give to a model, because at the end of the day it will be manipulating numbers, and you can design your inputs in as many ways as you want, and there are methods that just manipulate this input in order to give the output. So essentially using all the input, roughly speaking, or in a way that you may not be able to see if there is part of the input that it is most used or not. And then there are methods, including deep learning, that do first a manipulation of the input in order to achieve a internal or visible representation that is actually allowing then the model to make a kind of somewhat simple final model to make the prediction. So at the price to have done first the manipulation of the input. What we gain in this is that we can outsource to the machine learning this representation learning, but at some point we can inspect what representation has been learned, and we can use it so that we can use only the final part of the model if we find a way to do this morphing from the input to the representation that it is suitable. Or we may learn something from that representation, that it has certain symmetries that we didn't expect or something like that. So representation learning is becoming more and more interesting. I mean, that's also not a new idea. It was spelled out in the early 2000s, as soon as deep learning appeared, when people started to ask themselves why it was working so nicely. Fine, so I think this is it for the slides. What time is it? Yes, so you have questions so far? Or anything, expectations, or otherwise I essentially plan to go already into the first of the kind of general concept that I really think it is necessary to know for any advanced or not advanced machine learning kind of understanding. Okay, so okay, so what I want to I hope it is a recapitulation for all of you, but just to be sure, let me try to give somewhat detailed explanation of what is called as the bias, yes, variance, and often forgotten, yes, versus noise trade-off. Probably trade-off can be only between two things, so but in any way competition or something like that. So when we train a machine learning model, so this would be now a supervised learning. There are concepts of bias and variance also for unsupervised learning, but they are more ad hoc. What is very clear, if we are trying to predict labels, so we have data and we want to predict labels, we have different sources of errors, and this is what I will try to explain. And this aspect doesn't have anything to do with the model that class that we use. So it could be any kind of deep learning or any other model class in machine learning, right? So we just need to have data, so labeled data. So that means that we have pairs. Let's say Y's typically are always the output, the labels, and xi is the input. In a single task learning, you have that the output is a scalar. Even if it is a class, it's mapped into a number. So at the end of the day, it is a scalar. It is a number. And actually, more specifically, if it is a classification, what the model predicts is a probability to be in a certain class. So by all means, it is a number. And you have an input that can be of any dimension. So that's why I will try to always put an arrow on top of the input x. And then in general, we have a data set. So we have a collection of these pairs of labels and input. And now I need to define a few kind of well, I have to make a few definitions before I can define the errors that a certain model prediction can do, and then analyze what is what. So we have a data set of these pairs, and so these Y's in general are coming from a probability distribution to get a value of y given the input and parameters. So this is a formal way to say that every time you have a predictive model, a machine learning model, what that model is actually doing is taking an output from a probability distribution given the input or given the parameters of training. Now this is one thing that sometimes is misunderstood, and when I started looking into machine learning a few years ago, I had a hard time to really pinpoint in textbooks. The point is that, so why do we have a probabilistic model? Well, because the mathematics, so one justification is that the mathematics to make prediction, then we can use all statistics that has been developed that works nicely when you have random variables. So if you want to find the parameters that better explain the data, we have all the machinery if we interpret a model as something that makes a prediction out of a distribution. Besides that, it is not always given, even though ideally we would like for a given input to have a specific output. So every time you give the same input, you get a specific output. That's not reality, right? So if you do an experiment, you get a distribution, even if you think that you repeat the measure with exactly the same input, because of course the input is not the full knowledge of the wave function or whatever of the universe at that point. So there is uncertainty. There is uncertainty because you do not fully describe your input. So this is in your X. So be it a physical model or a statistical learning model where you just start from some input representation and then the model is learning something on the fly, that this representation is not complete. So there is not a single Y, there is a distribution of Ys. Right? So this is then ingrained in learning from data, machine learning, statistical learning, and so on. So first I have to define, so this given, I define one thing that is called expected labels. So label, I would say. So since we have a distribution, we can always define an average. So expected in the statistical sense is the average of our label. So I integrate formally my distribution given X over all possible outputs. So that would be my expectation value, right? So it's just I treat P of Y given X as a distribution. I evaluate the expectation value, and this is so I will use this capital E, special capital E for expectation values, because I will define a few in the next few minutes. So given Y. So given X. So we know X in some way, the input, and our output is a distribution, so we can always define the expected label. And so what we need later is that we will use the Y overscore, outscore. So that symbol. Then I define the expected test error, also called generalization error, given, because now then I define another one, given that we have trained a model. So this H is the model that has been trained on a specific data set, the D is above there, and then we are using the model for a specific input X. So we are given the model, we can define this expectation value, that is HD minus Y square, and this would be just an integral over all X and all Y's of this HD of the specific test input. So this would be just one input, and the actual output, so we know it because we are testing our model. So this is sometimes called ground truth. So we have a certain point, some pairs of X and Y where we know what is this. We have trained the model without using this test input, and then we look for this prediction, and then we have to integrate. So we have to multiply the probability of X and Y, and then the X dy. So this would be, probably I have to close this one. Yes. So we are integrating over the X and the Y that is predicted by the model in order to get the average test error for that given model, right? Yeah, probably. For the sake of clarity, I probably should put test everywhere, but okay, allow me not to. So I run over a set of test data. So this would be my expected test error. And then I would have the expected, this is very formal, the expected model. So again, expected in statistics means average, right? So this would be, we can define an average model that would be, so how do I change the model? I change the model by changing the training data, right? So that would be expectation value given the data of our models that depend on the data. And this is, so this is a kind of formal integral, but in principle it could be done analytically, meaning, so we need to know the probability distribution of the data and then integrate over them. In practice, it will be empirical, so we just sample training set and we do the average over all the. But now you will see why this is, all these definitions are important. So we allow that our model make an error. So once we fix the model with a certain training, it could give an error with respect to the ground truth. And we allow that if we change the training data, the actual model that we get is different, but we can still define an average model. We could also use it like, okay, we train all the models and then we take the average of that. If we would be able to know this distribution, we could also do that analytically, and there are cases in which we do, but most of the cases not. We just do empirically. So we sample training data and we define the expected model. And by the way, if you have heard ensemble modeling in machine learning, that's exactly what people do. So you train different models with different training data, and sometimes you change other specification of the model, and you get different models that do mistakes for different reasons, hopefully. So you average them to get something more robust. Next is the expected test error. So same name as before, but now given the model class A. So basically, also here, probably I should have specified given. So these are not all the possible models in the universe, but you define a model class, and so this is where you do this integration, because different training data will give different parameters of that model in the model class, and then you can do the average. And then you can also define the expected error now given the input, the output, and the data set, right? So here the expected error was given the input and output, but having fixed the data set to where you train. So having fixed the model, but now if we allow also a class, an ensemble of models, we can define also the expected test error over all the models. So we have HD minus y square. So would be integral now over all these things, so it's HD minus y, P of xy, P of t, and then everything. Okay, so all this was just to get to the different sources, not yet the sources of error, but different types of error that we can analyze. So we fix the data set, we get certain error, but if we also allow to sample different training sets, we have a different type of error that we expect. So now so this would be the most general error that we do, because we allow everything to change, and then we analyze this error. So here I will just hint at the mathematical trick, because I don't want to spend. Actually, the time is also almost over for today. But in any case, so here we what we do is to say that this error here we add and subtract, in this case, h bar, so h over bar. So let me just put all the parentheses in the same way. So this is the same, right? So I added and subtracted this h over bar. That is our expected model from here. But it doesn't matter. I just added and subtract the same quantity. It is a quantity, it's something well defined. And then here is what I spare, because we have, otherwise we have to write all the expansion of that square. This is equal to hd minus h square bar plus h bar minus y bar. So right. So basically, if you go and do all the double products, they cancel out because of the same reason. When you do the standard deviation, they cancel out. So it's something that in statistics you see over and over. What I need here is that I can now, so this is now expectation value of a sum, so I can decompose this. So I have an error that now doesn't depend on D, because D is fixed. So in this part here we have fixed D. So hd minus h, and then not the other way around. So there we have fixed D, so this depends on D. And so what is that? This is the expectation value of the square of the average model minus the prediction of the specific model squared. So that's the variance of the distribution of prediction from the different models when we change the data set. Right? So we change the data set every time we get the different models. It will have an average and it will have a standard deviation, or actually a variance. So, and this is what is called variance in machine learning, because it is a variance, but it is specifically the variance when we change the training set, and it can be extended when we change also certain parameters that are called hyperparameters. I will come back to that in our model. So basically we train different models by changing something in the way we train, and then they will have a distribution. This other part here, we basically do the same trick to add and subtract this time the ground, so the average, let me write it. So this one was bar, right? Otherwise, the above. Yes, there was a bar. H minus y. Yes, plus y minus y. So the y is the average for that particular input, and this is the actual input, the actual output, and then we have the average model. So this is the same, so there should be a square, of course, somewhere here, and this is equal for the same reason as before. The squares group and the double products, so they simplify, so we get this guy here. So I add this the step in which I do plus minus, just to see what is the mathematical idea behind, so that you see that we can decompose the overall error that is explicated here, expected test error given the model class, into variance, and then something that we call bias and something that we call noise. Okay, so let's have them all in the same screen. So this part of the error comes from the fact that we changed the training set. This part is the larger, the more the average evaluation of our different way to training the model differs from the actual truth, right? So that's a bias. Our model on average predicts something that is different from the actual value, and it has a distribution when we change the x, the input, and this is has the name of bias. Some textbook insist that this is bias square, because bias in principle is the square root of that. So sometimes you see bias square. And then there is another guy here that is often forgotten from the very beginning when people say variance bias trade-off. That is that in reality you can have a distribution of output, and you capture only the average of that distribution. So the noise. Do I have another noise? So this part is intrinsic, or better, depends on the representation X. Right. So we show briefly now and come back next time. We can do things to improve on variance and bias, but this noise here is kind of an expression of the lack of knowledge that we have from the input side, right? So if we want to improve on that, we typically have to completely redesign our model. And I close with the usual plot that I think you have seen many times, but hopefully now it becomes a bit more specific what it means. So we are capturing error versus something that is called the complexity of the model. So complexity is not easy to define. For the sake of this exposition, let's say it is just the number of training parameters that you have in your model, right? So a model will be more complex the more it will have training parameters from your data. And so if we want to quantify the errors, there will be a kind of overall offset that is our noise. Actually, in textbook you will find more the name of irreducible error. Again, that depends really on your input representation. You cannot go below that if you don't change the input representation. But sometimes your input representation is in your training data, right? So you get a table, and you often you cannot do more than that unless you can go back to the experiments. And then you have, yes, so this is the thing that you have seen so many times, bias and variance. So why bias has to decrease with complexity? Yeah, because you have more training parameters. So more training parameters means that you can tune your average so the expected model towards the actual truth for all the data at the same time. So this is what your learning is doing. More parameters you have to to tweak with, you can reduce this bias. So this is why, if you do things properly, your bias will reduce with the complexity of the model, while the variance will increase. Yeah, because you have more training parameters. So every single model has a chance to get more different results when for every specific choice of your training. And so that will typically increase. Sometimes it could be a little bit more like maybe there is a kind of plateau in when you increase complexity, because you may have some other things going on that avoid this increase in variance. But at the end, I mean, the prototypical behavior would be this one, and typically you would like to settle with the complexity that it is the one that is giving you a minimum error. That again would be a sum of irreducible bias and variance. So I would stop here. I have few more things to say about the variance bias trade-off, on how we train models in general. But for today, stop here. So I think it's also good. So next time I will briefly go through these ideas and conclude with what we actually, how we use these concepts to improve the training of our models. Yeah, thank you for today. And then stop.